Gravity shapes everything. It sculpts the paths of planets, bends the fabric of space, and pulls matter together from across the universe. It is the dominant force at cosmic scales, the architect of stars and galaxies. And yet, at the level of particles and atoms, gravity is so extraordinarily weak that the other forces of nature make it seem almost absent by comparison. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Tonight, we are going to sit with that paradox quietly and carefully. We will look at what gravity actually is, how it compares to the other fundamental forces, and why the gap between its cosmic dominance and its subatomic feebleness has puzzled physicists for over a century. We will consider what the universe looks like when you measure forces against each other with precision, and we will explore some of the ideas that have been put forward to explain why gravity behaves so differently from everything else. There are no final answers here. This is one of the genuinely open questions in physics, and that openness is part of what makes it worth spending a quiet evening with. So settle in. Let the ideas arrive slowly. There is no rush and nowhere else to be. Let's begin. Chapter 1. The force we feel. Gravity is the most familiar force in the universe. You have felt it every moment of your life, from the first breath you took to this very instant. It is the reason you stay in your chair, the reason water flows downhill, the reason the sky does not simply drift away into space. It is so constant, so unvarying, so thoroughly woven into the fabric of daily experience that most of the time you do not notice it at all. It is simply the background condition of being alive on a planet. And yet for most of human history, no one knew what gravity actually was. People knew it existed. They could measure its effects with reasonable precision long before they had any tools to do so formally. A stone dropped from a height falls. A thrown object curves back toward the ground. The moon does not fly off into the darkness. These observations were available to anyone who looked, and they were noted, recorded, and puzzled over for thousands of years before anyone produced an explanation that held together mathematically. The first person to do that with real rigor was Isaac Newton, working in the latter half of the 1600s. Newton did not discover gravity in the sense of noticing it for the first time. What he did was far more significant. He described it. He produced a mathematical framework that could predict the behavior of falling objects, orbiting moons, and distant planets using a single unified set of rules. His law of universal gravitation stated that every object with mass attracts every other object with mass, and that the strength of that attraction depends on how massive the objects are and how far apart they sit. The greater the mass, the stronger the pull. The greater the distance, the weaker it becomes, falling off with the square of the separation between them. This was a profound achievement. For the first time, the motion of a cannonball and the orbit of the moon could be described by the same equation. The heavens and the earth, which had for centuries been treated as fundamentally different realms operating under different rules, turned out to follow the same gravitational logic. Newton's framework held up extraordinarily well for over 200 years, and it still serves as a perfectly adequate description of gravity for most practical purposes today. But Newton himself was uncomfortable with one aspect of his own theory. His equations described how gravity behaved, but they offered no explanation for how it worked. How did the sun reach across 150 million kilometers of empty space and hold the Earth in its orbit? What was the mechanism? Newton famously refused to speculate. He wrote that he framed no hypotheses about the underlying cause, and that the mathematical description was sufficient for his purposes. It was an honest and careful position, but it left a question open that would not be properly addressed for another 2 centuries. That address came from Albert Einstein, whose general theory of relativity, published in 1915, offered a completely different picture of what gravity is. Where Newton had described gravity as a force reaching across space, Einstein described it as a consequence of the shape of space itself. Mass, in Einstein's framework, does not simply attract other mass at a distance. It curves the fabric of space-time around it, and other objects follow the paths that curvature creates. What we experience as the pull of gravity is not a pull at all in the traditional sense. It is the natural motion of objects through a curved geometry. This shift in understanding was not merely a refinement of Newton's picture. It was a fundamentally different way of thinking about what space, time, and matter are and how they relate to one another. Einstein's theory made predictions that Newton's could not, and those predictions have been confirmed repeatedly with extraordinary precision. The bending of light around massive objects, the slowing of time near large masses, the existence of gravitational waves rippling through space-time. All of these follow directly from general relativity, and all of them have been observed. So we now have 2 descriptions of gravity: Newton's, which is simple, practical, and accurate enough for most everyday situations, and Einstein's, which is deeper, stranger, and far more accurate when precision matters or when the gravitational fields involved are extremely strong. Both descriptions capture something real about how gravity behaves. Neither one, as we will see, fully explains why gravity is so extraordinarily weak compared to everything else that acts on matter at small scales. That question, why gravity is so feeble, begins to come into focus when you place it alongside the other fundamental forces of nature and measure them against each other. And when you do that comparison carefully, the result is one of the most startling numbers in all of physics. Chapter 2: Measuring the Forces. That number becomes clearer when you consider what it means to measure a force. In physics, forces are not simply described as strong or weak in casual terms. They are measured with precision, compared against each other using consistent units, and ranked according to how powerfully they act on particles at a given scale. When you apply that kind of rigorous comparison to the 4 fundamental forces of nature, gravity does not merely come last. It comes last by a margin so extreme that it barely seems to belong in the same conversation as the others. The 4 fundamental forces are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each one governs a different aspect of how matter and energy interact. The strong nuclear force binds the nuclei of atoms together, holding protons and neutrons in tight formation against the electrical repulsion that would otherwise push them apart. The weak nuclear force governs certain kinds of radioactive decay and plays a central role in the nuclear reactions that power stars. Electromagnetism governs the interactions between charged particles, binding electrons to atoms, allowing chemical bonds to form, and producing the full spectrum of light and radiation that fills the universe. And gravity governs the attraction between masses, shaping the large-scale structure of everything from planets to galaxy clusters. At first glance, this sounds like a reasonably balanced set of responsibilities. Each force has its domain. Each one contributes something essential to the way the universe works. But when you measure their relative strengths at the scale of subatomic particles, the balance collapses entirely. The strong nuclear force is roughly 100 times more powerful than electromagnetism at that scale. The weak nuclear force is weaker than electromagnetism, but still vastly more powerful than gravity. And gravity itself sits so far below the others that expressing the gap requires numbers that are genuinely difficult to hold in the mind. The gravitational attraction between two protons, for example, is approximately 10 to the power of 36 times weaker than the electromagnetic repulsion between them. That is a 1 followed by 36 zeros. If you tried to represent that ratio physically, with gravity as a single step, and electromagnetism as a distance proportional to its strength, electromagnetism would stretch from here to a point far beyond the observable universe. The gap is not merely large. It is so large that it raises an immediate and uncomfortable question. Why should one of the four fundamental forces be so extraordinarily different from the others? What does that gap mean? And is it a clue to something deeper about the structure of reality? To appreciate the full strangeness of this gap, it helps to consider what forces actually do at the particle level. When two electrons come near each other, they repel with immediate and measurable force. The electromagnetic interaction between them is precisely described by the equations of quantum electrodynamics, one of the most accurate theories ever produced in science. When quarks interact through the strong nuclear force inside a proton, the binding is so intense that pulling them apart entirely would require enough energy to create new particles from scratch. These are not gentle or subtle interactions. They are fierce, dominant, and precisely measurable at small scales. Gravity, by contrast, is so weak at the particle level that it plays no meaningful role in atomic or subatomic physics. No calculation in particle physics needs to include the gravitational attraction between individual particles. Its contribution is so vanishingly small that including it would change no measurable result. At the scale of atoms and their constituents, gravity is not merely weaker than the other forces. It is so far below them that it effectively disappears from the equations entirely. This creates a profound asymmetry at the heart of physics. The universe we experience at human scales is shaped overwhelmingly by gravity, because gravity is the only long-range force that accumulates with mass without cancelling itself out. Electromagnetism is also a long-range force, but positive and negative charges tend to balance each other in large neutral objects, leaving the net electromagnetic effect between planets or stars close to zero. Gravity carries no such cancellation. Every particle of mass adds to the total gravitational pull without any opposing sign to reduce it. So even though gravity is extraordinarily weak per unit of mass, it becomes the dominant force at large scales simply because mass gathers in such enormous quantities. At small scales, however, the situation reverses completely. A single proton feels the electromagnetic force, the strong nuclear force, and the weak nuclear force with enormous intensity. It feels gravity so feebly that the gravitational interaction between two protons is, for every conceivable experimental purpose, completely unmeasurable with any instrument we currently possess. The force that assembles galaxies is invisible at the scale of the particles those galaxies are built from. That complete reversal of dominance, depending entirely on the scale at which you are looking, is not merely a curiosity. It is one of the deepest unresolved tensions in the whole of modern physics. Physicists have a name for this tension. They call it the hierarchy problem. It is not simply the observation that gravity is weak. It is the deeper question of why the gap between gravity and the other forces is so extraordinarily, specifically, and precisely large. A ratio of 10 to the 36 does not appear by accident in a coherent theory of nature. Numbers that extreme demand an explanation. They suggest that something fundamental is either missing from our current picture or is being expressed in a form we have not yet learned to read correctly. The hierarchy problem has been one of the central motivating puzzles of theoretical physics for several decades. It has driven the development of entire frameworks, inspired proposals about the structure of space itself, and shaped the questions physicists chose to ask when designing the most powerful particle accelerators ever built. None of those efforts has yet produced a universally accepted answer, but each one has deepened our understanding of the question, and that deepening is itself a form of progress, even when the final resolution remains out of reach. What makes the hierarchy problem especially striking is that it does not arise from a lack of precision in our measurements. We know with great accuracy how strong each of the fundamental forces is. The gap between gravity and the others is not an artifact of uncertainty or experimental error. It is a real, measured, confirmed feature of the universe. The question is not whether the gap exists. The question is what it means, and whether the answer lies within the physics we already understand or somewhere beyond it. Looking further, there is another layer to this puzzle that becomes visible when you consider not just the strength of the forces, but the particles that carry them. In the modern framework of particle physics, forces are understood as being transmitted by special particles called gauge bosons. Electromagnetism is carried by the photon. The strong nuclear force is carried by particles called gluons. The weak nuclear force is carried by the W and Z bosons. And gravity, if it follows the same pattern, should be carried by a particle called the graviton. That particle has never been directly detected, and the theoretical difficulties involved in describing gravity in particle terms are themselves a reflection of the same deep asymmetry we have been exploring. The other three forces fit naturally into a framework called the Standard Model of Particle Physics, which describes their carriers, their interactions, and their behaviors with extraordinary mathematical precision. Gravity does not fit into that framework. Every serious attempt to incorporate gravity into quantum field theory in the same way as the other forces has run into fundamental mathematical difficulties. The equations produce nonsensical infinities that cannot be resolved by the same techniques used to handle similar problems in electromagnetism and the nuclear forces. This failure is not a technical detail. It is a signal that something about the way we are thinking about gravity is incomplete, and that the incompleteness may be directly related to why gravity is so different in strength from everything else. We will explore those attempts and their difficulties in the chapters ahead. For now, it is enough to hold this picture in mind. 4 forces govern the universe. 3 of them fit together in a single coherent mathematical framework and act with comparable strength at small scales. The 4th stands entirely apart, weaker by a factor of 36 orders of magnitude, resistant to every attempt to bring it into the same theoretical fold, and dominant only at the larger scales, where the other forces have effectively cancelled themselves into silence. That is the landscape we are working within, and it is a genuinely strange one. Chapter 3: Einstein's Curved Space. To understand why gravity sits so far apart from the other forces, it helps to understand what gravity actually is in the deepest description we currently have. And that description comes from Albert Einstein, whose general theory of relativity transformed gravity from a force into a geometry. Before Einstein, the picture inherited from Newton was one of action at a distance. Mass attracted mass across empty space, and the strength of that attraction followed a precise mathematical rule. The picture worked beautifully for predicting the motions of planets, the behavior of falling objects, and the trajectories of comets, but it offered no mechanism. There was no explanation for how the sun reached across 150 million kilometers of vacuum and held the Earth in its path. Newton himself acknowledged this openly, and generations of physicists after him accepted the mathematical description while quietly setting aside the question of how it actually worked. Einstein answered that question, though his answer required abandoning some of the most deeply held assumptions about the nature of space and time. His special theory of relativity, developed in 1905, had already established that space and time are not separate independent quantities, but are woven together into a single four-dimensional fabric called spacetime. The passage of time and the measurement of distances are not absolute. They depend on the relative motion of the observer. This was strange enough. But the general theory of relativity, completed a decade later in 1915, went further still. General relativity proposed that spacetime is not a fixed, rigid background against which events unfold. It is a dynamic, flexible structure that can be curved and warped by the presence of mass and energy. A massive object like the Sun does not reach out across space to pull the Earth toward it. Instead, the Sun's mass curves the spacetime around it, and the Earth follows the straightest possible path through that curved geometry. What we experience as the gravitational pull of the Sun is simply the Earth doing what all objects do in curved spacetime, which is to follow the path of least resistance through the geometry that mass has created. This is a genuinely difficult idea to hold in the mind, because our intuitions about space are built from experience in a world where curvature is mostly invisible. A useful approximation is to imagine a heavy ball placed on a stretched rubber sheet. The ball creates a depression, a curve in the surface, and smaller objects rolling nearby follow paths that curve toward the depression. The analogy is imperfect in many ways, but it captures something of the essential idea. Mass curves the medium, and other objects respond to that curvature rather than to any direct pull. In Einstein's framework, gravity is not a force in the traditional sense at all. It is a consequence of geometry. Objects in free fall, like the Earth orbiting the Sun, or an astronaut floating in a spacecraft, are not being pushed or pulled by anything. They are following what physicists call geodesics, the straightest possible paths through curved spacetime. The reason a falling apple accelerates toward the ground is not that the Earth is pulling it. It is that the Earth's mass has curved the spacetime around it in such a way that the apple's natural path through that geometry leads toward the surface. This reframing has profound consequences. It means that gravity is fundamentally different in character from the other three forces. Electromagnetism, the strong nuclear force, and the weak nuclear force are all described in the language of quantum field theory as interactions between particles mediated by the exchange of other particles. They are forces in the traditional sense, pushing and pulling on charged or interacting particles through the exchange of gauge bosons. Gravity, as described by general relativity, is not that kind of thing at all. It is not an interaction between particles in a background space. It is a property of the background space itself. This distinction is not merely philosophical. It has direct mathematical consequences. When physicists tried to describe the other three forces within the framework of quantum mechanics, the mathematics works. The descriptions are complicated and require sophisticated techniques, but they produce finite, meaningful answers that match experimental results with extraordinary precision. When physicists tried to describe gravity within the same quantum mechanical framework, the mathematics breaks down. The calculations produce infinities that cannot be removed by the techniques that work for the other forces. General relativity and quantum mechanics are both extraordinarily successful theories within their respective domains, but they are mathematically incompatible when pushed into the same territory. This incompatibility is one of the central problems of modern theoretical physics, and it is intimately connected to the question of gravity's weakness. The other forces have quantum descriptions because they are, at their core, interactions between particles in a fixed space-time background. Gravity resists a quantum description because it is not an interaction in space-time. It is space-time. Quantizing gravity means quantizing the geometry of space and time itself, and no one has yet found a fully consistent way to do that. Several approaches have been attempted. String theory proposes that the fundamental constituents of nature are not point particles, but tiny vibrating strings of energy, and that one of the vibrational modes of these strings corresponds to the graviton, the hypothetical carrier of gravity. Loop quantum gravity proposes that space-time itself is made of discrete quantum units at the smaller scales, and that the smooth curved geometry of general relativity emerges from the collective behavior of these units at larger scales. Both approaches have produced interesting mathematics and partial insights, but neither has yet delivered a complete, experimentally confirmed theory of quantum gravity. What is striking about this situation is how cleanly it maps onto the question of gravity's weakness. The forces that have successful quantum descriptions are the strong forces, the ones that dominate at small scales. The force that resists quantum description is the weak one, the one that dominates only at large scales, where quantum effects are negligible. Whether this parallel is a coincidence or a deep structural connection is one of the questions that a future theory of quantum gravity might eventually answer. For now, what general relativity gives us is a precise and beautiful description of gravity at the scales where it matters most, which is to say at the scales of planets, stars, galaxies, and the universe as a whole. It tells us that space-time is curved by mass and energy, that objects follow geodesics through that curved geometry, and that the curvature itself evolves dynamically as matter moves and energy flows. It predicts gravitational waves, the rippling distortions of space-time produced by accelerating masses, which were first directly detected in 2015 by the LIGO Observatory. It predicts the existence of black holes, regions where the curvature of space-time becomes so extreme that nothing, not even light, can follow a geodesic that leads back out. It predicts that time passes more slowly in stronger gravitational fields, an effect measurable with atomic clocks and directly relevant to the functioning of GPS satellites. All of these predictions have been confirmed. General relativity is one of the most precisely tested theories in the history of science, and yet it tells us nothing about why gravity is so weak. The strength of gravity enters the theory as a parameter, a number called Newton's gravitational constant, which has to be measured experimentally and inserted into the equations by hand. The theory does not derive that number from anything more fundamental. It simply accepts it as a given feature of the universe and works from there. That acceptance is precisely what the hierarchy problem challenges. If gravity's weakness is not explained by our best theory of gravity, then the explanation must lie somewhere else. It must lie in whatever deeper framework eventually unifies gravity with the other forces, or in some structural feature of the universe that general relativity and the Standard Model together do not yet capture. Finding that explanation is one of the great open tasks of theoretical physics, and the chapters ahead will explore the most serious attempts that have been made to meet it. Chapter 4. The Hierarchy Problem. There is a question that sits at the heart of modern physics, and it is not the kind of question that announces itself dramatically. It arrives quietly, almost mathematically, as a simple observation about two numbers. The first number is the strength of gravity. The second number is the strength of the other fundamental forces. And the question is simply this: why are those two numbers so different from each other? This is the hierarchy problem, and it is worth taking a moment to understand why physicists find it so deeply unsatisfying. In a well-constructed theory of nature, the fundamental parameters that appear in the equations should either be derivable from more basic principles or should be natural in the sense of being close to one. A parameter that is enormously large or enormously small without any explanation for why it takes that value is a sign that something is missing from the theory. It suggests that the number is not truly fundamental, but is instead the result of some deeper mechanism that the theory has not yet accounted for. The strength of gravity is expressed in physics through a quantity called Newton's gravitational constant, usually written as g. When you compare g to the equivalent constants that describe the strengths of the other forces, the ratio is not merely large. It is so large that it sits in a category of its own. The electromagnetic force between two electrons is roughly 10 to the power of 42 times stronger than the gravitational force between them. The strong nuclear force is stronger still. These are not differences of degree. They are differences of kind, and they demand an explanation that goes beyond simply measuring the values and recording them. What makes the hierarchy problem especially acute is something that happens when you try to calculate the mass of the Higgs boson within the framework of quantum field theory. The Higgs boson is the particle associated with the Higgs field, which gives mass to the other fundamental particles. Its mass has been measured experimentally, and the value is relatively modest on the scale of particle physics. But when you try to calculate that mass theoretically, you find that quantum corrections, contributions from virtual particles that briefly pop into existence and then annihilate, tend to drive the Higgs mass upward toward the highest energy scale in the theory. And the highest natural energy scale in physics is the Planck scale, the scale at which quantum gravitational effects become important. The Planck scale is roughly 10 to the power of 19 times larger than the energy scale at which the Higgs boson actually lives. For the Higgs mass to remain as small as it is observed to be, these quantum corrections must cancel each other with extraordinary precision. The cancellation required is so fine that it amounts to adjusting two enormous numbers so that they differ by only a tiny amount. This kind of cancellation is not impossible in principle, but it strikes most physicists as deeply implausible without some underlying mechanism to enforce it. A theory that requires such extreme fine-tuning to reproduce observed reality is generally considered to be signaling that it is incomplete. This fine-tuning problem is sometimes called the naturalness problem, and it is closely related to the hierarchy problem. Both arise from the same basic tension between the scale of gravity and the scale of the other forces. The Planck scale, which is set by the strength of gravity, is so far removed from the scales at which the other forces operate that connecting the two without extreme fine-tuning seems to require new physics, some mechanism or principle that explains the gap rather than simply accepting it. One way to think about this is to imagine that you are building a bridge between two cliffs. The cliffs represent the two energy scales, the electroweak scale where the Higgs boson lives, and the Planck scale where gravity becomes strong. In a natural theory, the bridge would be roughly the same length as the height of the cliffs. But in the case of the hierarchy problem, the cliffs are separated by a distance of roughly 17 orders of magnitude, and the bridge has to span that entire gulf without any obvious structural support. Something has to hold it up, and whatever that something is, it is not visible in our current theories. Physicists have proposed several candidates for that structural support. Supersymmetry is one of the most extensively studied. It proposes that every particle in the Standard Model has a partner particle with different spin properties, and that the quantum corrections to the Higgs mass from ordinary particles and their supersymmetric partners cancel each other naturally without requiring fine-tuning. Supersymmetry is mathematically elegant and solves the naturalness problem neatly, but the partner particles it predicts have not been observed at the energies explored by the Large Hadron Collider, which has pushed the lower bounds on their masses high enough to create tension with the simplest versions of the theory. Another candidate is the idea of extra dimensions, which we will explore in more detail in a later chapter. The essential proposal is that gravity appears weak in our observable dimensions because it is spreading itself across additional dimensions that the other forces cannot access. In this picture, gravity is not intrinsically weak. It simply appears weak because most of its strength is being diluted into directions we cannot directly observe. This idea has the appealing feature of explaining the hierarchy as a geometric effect rather than requiring any fine-tuning of fundamental parameters. A third approach, less focused on solving the fine-tuning problem and more focused on accepting it, comes from the anthropic principle. This line of reasoning suggests that the hierarchy we observe may simply be one of many possible values in a vast landscape of possible universes, and that we find ourselves in a universe with this particular hierarchy because it is one of the configurations that allows complex structures and ultimately observers to exist. A universe in which gravity were much stronger would collapse too quickly for stars and galaxies to form. A universe in which gravity were much weaker might never allow matter to clump together into the structures needed for chemistry and life. The hierarchy we observe may be, on this view, a selection effect rather than something requiring a dynamical explanation. Most physicists find the anthropic approach unsatisfying as a final answer, though it cannot be ruled out. It trades a dynamical explanation for a statistical one, and it requires the existence of a vast ensemble of other universes that are by definition unobservable. Whether that trade is philosophically acceptable depends on what you think science is ultimately for, and that is a question that goes beyond physics into the territory of epistemology and the philosophy of science. What is clear is that the hierarchy problem is real, that it reflects a genuine and deep tension in our current understanding, and that resolving it will almost certainly require new physics beyond the Standard Model. The question is not whether that new physics exists. The question is what form it takes and when our experiments will become sensitive enough to reveal it. Chapter 5. Supersymmetry's Promise. Of all the proposals put forward to explain the hierarchy problem, supersymmetry is the one that has attracted the most sustained attention from theoretical physicists over the past several decades. It is mathematically elegant, it addresses the fine-tuning problem directly, and it makes predictions that are in principle testable with particle accelerators. It is also, as of the time of writing, unconfirmed by experiment. That combination of theoretical appeal and experimental silence makes supersymmetry one of the most discussed and most debated ideas in all of modern physics. The core idea of supersymmetry is a proposed symmetry between two fundamental categories of particles. In the Standard Model, all particles fall into one of two classes. Fermions are particles with half-integer spin, and they include the quarks and leptons that make up ordinary matter. Bosons are particles with integer spin, and they include the gauge bosons that carry the fundamental forces as well as the Higgs boson. Fermions and bosons behave very differently. Fermions obey the Pauli exclusion principle. which prevents two identical fermions from occupying the same quantum state, and this is ultimately why matter has solidity and structure. Bosons do not obey this principle, which is why many photons can occupy the same state and why lasers work. Supersymmetry proposes that there is a deep symmetry connecting these two classes. For every fermion in the Standard Model, supersymmetry predicts the existence of a corresponding boson partner, and for every boson, a corresponding fermion partner. These partner particles are called superpartners, and they would have the same mass and charge as their Standard Model counterparts, but different spin. The superpartner of the electron, for example, is called the selectron. The superpartner of the quark is the squark. The superpartner of the photon is the photino. The naming conventions are not subtle, but the mathematics underlying them is anything but simple. The reason supersymmetry is relevant to the hierarchy problem is that the quantum corrections to the Higgs mass from fermions and bosons have opposite signs. Fermion loops in the quantum calculation push the Higgs mass upward, while boson loops push it downward. In a supersymmetric theory, every fermion has a boson partner with exactly the right properties to cancel its contribution to the Higgs mass, and vice versa. The cancellation is not accidental or fine-tuned. It is enforced by the symmetry itself. If supersymmetry is exact, the Higgs mass receives no large quantum corrections at all, and the hierarchy problem simply dissolves. The difficulty is that supersymmetry cannot be exact in nature, because we do not observe superpartners with the same mass as their Standard Model counterparts. If the selectron had the same mass as the electron, we would have detected it long ago. So if supersymmetry exists, it must be broken, meaning that the superpartners are heavier than their Standard Model counterparts by some amount. The cancellation of quantum corrections is then not perfect, but approximate, and the degree of approximation depends on how heavy the superpartners are. If they are too heavy, the cancellation is not good enough to solve the hierarchy problem without reintroducing some fine-tuning. This is where the experimental situation becomes uncomfortable. The Large Hadron Collider at CERN, which began operations in 2008 and has been running at increasing energies ever since, was widely expected to find superpartners if they exist at masses light enough to solve the hierarchy problem naturally. So far, no superpartners have been found. The lower bounds on their masses have been pushed steadily higher with each passing year of data collection, and the simplest versions of supersymmetry, the ones that most cleanly solve the hierarchy problem, are under significant pressure. This does not mean supersymmetry is wrong. The theory has many variants, and some of them place superpartners at masses beyond the current reach of the Large Hadron Collider. It is entirely possible that supersymmetry exists, but that the energy required to produce superpartners is simply higher than what current accelerators can achieve. Future experiments, including potential higher energy colliders that have been proposed but not yet built, might still find the signatures that supersymmetry predicts. The absence of evidence is not the same as evidence of absence, particularly when the search is ongoing and the parameter space of the theory is large. What supersymmetry also offers, beyond its solution to the hierarchy problem, is a natural candidate for dark matter. The lightest superpartner in many versions of the theory would be stable, weakly interacting, and massive, which are precisely the properties that a dark matter particle needs to have to match astronomical observations. This is sometimes called the WIMP miracle, where WIMP stands for weakly interacting massive particle, and it adds an additional motivation for taking supersymmetry seriously, even as its direct experimental signatures remain elusive. There is also a deeper mathematical motivation. Supersymmetry is the only possible extension of the symmetries of spacetime that is consistent with the general principles of quantum field theory, according to a theorem proved in the 1970s by physicists Haag, Lopusanski, and Sonius. This means that if nature makes use of all the symmetries available to it, as it has consistently done in every other domain of physics, then supersymmetry should be part of the picture somewhere. Whether it is broken at energies accessible to current experiments or at energies far beyond our reach, is a question that only more powerful accelerators can answer. For now, supersymmetry occupies a curious position in theoretical physics. It is too mathematically compelling to dismiss and too experimentally elusive to confirm. It sits at the edge of what we know, pointing toward a possible resolution of the hierarchy problem, while declining to reveal itself directly. That is an uncomfortable place for a theory to sit, but it is not an unfamiliar one in the history of physics. Many of the deepest ideas took decades to find experimental confirmation, and some of the most important features of the universe were theoretically predicted long before the instruments existed to detect them. Chapter 6: Extra Dimensions. One of the most striking proposals ever made in theoretical physics is also one of the simplest to state. What if the universe has more dimensions than the three spatial ones we can see and move through? What if gravity appears weak, not because it is intrinsically feeble, but because it is spreading itself across additional dimensions that are hidden from our direct experience? This idea, developed in various forms over the past century and refined significantly in the late 1990s, offers a genuinely different way of thinking about the hierarchy problem, one that replaces fine-tuning with geometry. The notion of extra dimensions has a long history in physics. The first serious proposal came from Theodore Kaluza in 1921, when he showed that if you add a fifth spatial dimension to Einstein's general relativity, the equations naturally split into two parts. One part reproduces Einstein's original gravitational equations in 4 dimensions. The other part reproduces Maxwell's equations for electromagnetism. Kaluza had unified gravity and electromagnetism using nothing more than an extra dimension of space. The result was elegant enough that Einstein himself spent years exploring its implications. The obvious question was why we do not notice this extra dimension. Oscar Klein provided an answer in 1926. He proposed that the extra dimension is curled up into a tiny circle, so small that no experiment at the time could possibly detect it. If the radius of this circle is small enough, the extra dimension is effectively invisible at the energies and distances accessible to ordinary observation. The Kaluza-Klein proposal, as it came to be known, introduced the idea that extra dimensions could exist but remain hidden by virtue of their compactness, and this idea became a central tool in theoretical physics for decades to come. The modern revival of extra dimensions as a solution to the hierarchy problem came from work by Nima Arkani-Hamed, Savas Dimopoulos, and Gia Dvali in 1998, in a proposal usually referred to by the initials ADD after its authors' surnames. Their key insight was that the extra dimensions do not need to be as small as Kaluza and Klein had imagined. If the other forces of nature are confined to a 3-dimensional surface, sometimes called a brane, embedded in a higher dimensional space, then only gravity propagates through the full higher dimensional volume. The other forces never feel the extra dimensions at all, which is why their behavior is fully described by physics in 3 spatial dimensions. In this picture, gravity appears weak because it is the only force diluting itself across the extra dimensions. The true strength of gravity in the full higher dimensional space might be comparable to the strength of the other forces. What we measure as the weakness of gravity in our three-dimensional experience is simply a consequence of that dilution. The gravitational force lines spread out in all available directions, including the extra ones, and so, by the time they reach us, they have been thinned to a fraction of their original intensity. The hierarchy is not a fundamental feature of nature. It is a geometric artifact of the way gravity propagates in a higher dimensional space. The ADD proposal made a striking prediction. If extra dimensions exist at a large enough scale, gravity should start to behave differently at short distances. At separations smaller than the size of the extra dimensions, gravity would no longer follow the familiar inverse square law. It would fall off more steeply with distance, reflecting the additional directions into which the gravitational force lines are spreading. This deviation from the inverse square law is in principle measurable with precision experiments that test gravity at very short ranges. Such experiments have been conducted, and they have found no deviation from the inverse square law down to distances of roughly 1/10 of a millimeter. This places constraints on the size of any large extra dimensions. For the ADD mechanism to explain the full hierarchy between gravity and the other forces, the extra dimensions would need to be large enough to produce observable deviations, and the absence of such deviations has ruled out some of the simplest versions of the proposal. However, the constraints depend on how many extra dimensions are assumed to exist, and versions of the theory with more extra dimensions remain consistent with current experimental bounds. A different approach to extra dimensions was proposed by Lisa Randall and Raman Sundram in 1999. Their model, known as the Randall-Sundram model, involves a single extra dimension that is not large but is curved in a specific way. In their picture, spacetime consists of two three-dimensional branes separated by a gap in the extra dimension. We live on one brane, and the geometry of the extra dimension is such that it warps the effective energy scales between the two branes exponentially. A modest separation between the branes in the extra dimension translates into an enormous difference in energy scales in the three-dimensional physics we observe. The hierarchy between gravity and the other forces emerges naturally from this exponential warping without requiring any fine-tuning of parameters. The Randall-Sundram model made predictions for the Large Hadron Collider, including the possible production of new particles called Kaluza-Klein gravitons, which are the higher dimensional analogues of the graviton spread across the extra dimension. These particles have not been observed, which constrains the parameter space of the model, but does not rule it out entirely. As with supersymmetry, the absence of a signal pushes the predicted new physics to higher energies, but does not eliminate the underlying idea. What both the ADD and Randall-Sundram proposals share is a fundamental shift in perspective on the hierarchy problem. Rather than asking why gravity is weak, they ask whether gravity is actually weak at all in the full dimensionality of space. The answer they suggest is that it is not. Gravity only appears weak because we are confined to a slice of a larger space and are measuring only the fraction of gravity's true strength that reaches us through that slice. The rest is out there, spreading through dimensions we cannot access directly, governing physics at scales we have not yet been able to probe. This is a genuinely different kind of explanation from supersymmetry. Supersymmetry addresses the hierarchy by cancelling the quantum corrections that would otherwise destabilize it. Extra dimensions address it by dissolving the hierarchy entirely, replacing it with a geometric relationship between scales that makes the apparent weakness of gravity a natural consequence of the structure of space itself. Whether either approach, or some combination of them, or something else entirely, turns out to be correct is a question that remains open, but both have deepened our understanding of what the hierarchy problem actually is and what kind of solution it might require. Chapter 7. The Graviton Question. Every force in the Standard Model has a carrier particle. Electromagnetism is carried by the photon, a massless particle that travels at the speed of light and can propagate across any distance without losing its identity. The strong nuclear force is carried by gluons, which bind quarks together inside protons and neutrons with extraordinary intensity. The weak nuclear force is carried by the W and Z bosons, which are massive particles with a very short range, responsible for the radioactive decay processes that power the sun and transform one type of particle into another. Each of these carrier particles has been detected experimentally, their properties measured with precision, and their behavior described with mathematical accuracy within the framework of quantum field theory. Gravity, if it follows the same pattern, should also have a carrier particle. That particle is called the graviton, and it has been a part of theoretical physics for decades. Its predicted properties follow from the requirements of the theory. It should be massless, like the photon, because gravity has an infinite range. It should travel at the speed of light, which is consistent with the observation that gravitational waves propagate at exactly that speed, confirmed when the detection of gravitational waves from a neutron-star merger in 2017 was accompanied by a simultaneous detection of light from the same event. It should have a spin of 2, which distinguishes it from all the other gauge bosons, which have spin 1, and from the Higgs boson, which has spin 0. And it should couple to energy and momentum universally, meaning that it interacts with everything that has energy, which is consistent with the observed universality of gravity. All of these predicted properties are theoretically well motivated. The problem is that the graviton has never been detected, and there are strong reasons to believe it may never be directly detected with any technology that could realistically be built. The reason comes down to the extraordinary weakness of gravity at the particle level, which is precisely the puzzle we have been exploring throughout this script. Because gravity is so weak, the interaction of a single graviton with a detector would be vanishingly faint. To detect even a single graviton with reasonable confidence, a detector would need to be so massive and so sensitive that it would collapse under its own gravity into a black hole before it could record a signal. This is not a practical limitation that better engineering might overcome. It is a fundamental constraint built into the structure of the theory. The impossibility of directly detecting individual gravitons does not mean gravity has no quantum nature. It means that our access to that quantum nature is severely limited by the very weakness that defines gravity's place among the forces. We can detect gravitational waves, which are classical ripples in spacetime produced by the bulk motion of enormous masses, but these are collective phenomena involving vast numbers of gravitons in the same way that a radio wave involves vast numbers of photons. The individual quantum of the gravitational field remains beyond reach. This situation creates a peculiar asymmetry in our knowledge. For the other three forces, we have direct experimental access to the carrier particles. We can produce photons, gluons, and W and Z bosons in laboratories, measure their properties, and test the predictions of quantum field theory with extraordinary precision. For gravity, we are limited to observing its classical effects at large scales, and the quantum regime remains theoretically described but experimentally inaccessible. We believe the graviton exists because the logic of quantum field theory strongly suggests it should, and because gravity behaves in ways that are consistent with a quantum description at the level we can probe. But we cannot confirm its existence the way we have confirmed the existence of every other fundamental particle. The theoretical difficulties with the graviton go deeper than the practical challenges of detection. When physicists try to build a quantum field theory of gravity using the graviton as the carrier particle, the calculations run into serious mathematical problems. In quantum electrodynamics, the theory of the electromagnetic force, certain calculations initially produce infinite results. These infinities can be removed by a procedure called renormalization, which involves carefully redefining the parameters of the theory in a way that absorbs the infinities into unmeasurable quantities, leaving finite and physically meaningful predictions for everything that can actually be observed. This procedure works for electromagnetism, the weak force and the strong force. It does not work for gravity. When you try to renormalize quantum gravity in the same way, the infinities that appear cannot be absorbed. New infinities keep appearing at each order of the calculation, requiring new parameters to absorb them, and there is no end to the process. A theory that requires infinitely many parameters to be fixed by experiment is not a predictive theory at all. It is, in a technical sense, non-renormalizable, and this non-renormalizability is one of the most fundamental obstacles to treating gravity as a quantum field theory, in the same way as the other forces. The non-renormalizability of gravity is not a technical accident. It is a symptom of the same deep tension we have been circling throughout this exploration. General relativity describes gravity as a property of spacetime geometry, not as an interaction in a fixed background spacetime. Quantum field theory, on the other hand, is built on the assumption of a fixed background spacetime in which fields propagate and particles interact. Trying to apply quantum field theory to gravity means trying to quantize the very background that quantum field theory assumes to be fixed, and the mathematics resists this with a consistency that suggests the resistance is telling us something important. String theory addresses this problem in a specific way. In string theory, the graviton is not a point particle, but a particular vibrational mode of a one-dimensional string. The extended nature of the string smooths out the short-distance behavior that causes the infinities in point-particle quantum gravity, and the resulting theory is finite and consistent, at least in some formulations. This is one of the most compelling arguments for string theory as a framework for quantum gravity, and it has motivated an enormous amount of research over the past 4 decades. However, string theory operates at energy scales far beyond any current or foreseeable experiment, and its connection to observable physics remains a subject of active and sometimes contentious debate. Loop quantum gravity takes a different approach, abandoning the idea of a smooth, continuous spacetime at the smaller scales and replacing it with a discrete network of quantum geometric elements. In this picture, space itself is made of tiny, indivisible units, and the smooth, curved geometry of general relativity emerges from their collective behavior at larger scales, much as the smooth surface of a liquid emerges from the discrete behavior of individual molecules. The graviton, in this framework, is not a fundamental particle, but an emergent phenomenon, a low-energy approximation to the underlying discrete quantum geometry. Loop quantum gravity avoids some of the problems of point-particle quantum gravity, but it has its own mathematical challenges, and it hasn't yet produced a complete and fully consistent theory that connects smoothly to the predictions of general relativity in all regimes. What both approaches share is an acknowledgement that the graviton question is not simply a matter of finding a new particle to add to the standard model. It requires a fundamental rethinking of what space, time, and quantum mechanics mean at the deepest level. The graviton is not just a carrier particle. It is, if it exists in the way the theory suggests, a quantum of spacetime geometry itself. And understanding what that means may require conceptual tools that have not yet been invented. Chapter 8: Strings and Loops. The two most developed attempts to build a theory of quantum gravity go by the names string theory and loop quantum gravity. They are very different in their starting assumptions, their mathematical structure, and their philosophical outlook. What they share is an ambition to describe gravity in a way that is consistent with quantum mechanics, and a recognition that doing so requires going beyond everything that current physics has established. Both have produced remarkable mathematics and genuine insights. Neither has yet produced a complete theory that can be tested against experiment in a decisive way. And both, in different ways, shed light on the question of why gravity is so different from the other forces. String theory begins with a deceptively simple modification of the standard picture of particle physics. Instead of treating the fundamental constituents of matter and energy as point particles with no internal structure, string theory proposes that they are tiny one-dimensional objects, strings of energy that vibrate at different frequencies. The different vibrational modes of a string correspond to different particles. A string vibrating in one mode appears as an electron. Vibrating in another mode, it appears as a quark. Vibrating in yet another mode, it appears as a photon. And one particular vibrational mode corresponds to a massless spin-2 particle, which is precisely the graviton. In string theory, gravity is not added to the theory by hand. It emerges automatically from the mathematics of vibrating strings. This automatic emergence of gravity is one of the most celebrated features of string theory. Every consistent quantum theory of strings necessarily contains a graviton, and therefore necessarily contains gravity. The other forces also emerge from the string framework as different vibrational modes, or as the dynamics of higher dimensional objects called branes. The dream of a unified theory, one framework that describes all forces and all particles from a single set of principles, seems within reach in string theory in a way that it does not in any other approach. The consistency of string theory, however, requires the existence of extra dimensions. The mathematics of string theory only works without internal contradictions in 10 dimensions, 9 spatial and 1 temporal. Some versions of the theory, known collectively as M-theory, require 11 dimensions. The extra dimensions beyond our familiar 3 must be compactified, curled up into shapes too small to detect directly, in a manner reminiscent of the original Kaluza-Klein proposal. The specific shape of these compactified dimensions determines the effective physics in the 4 dimensions we observe, including the strengths of the forces and the masses of the particles. This connection between the geometry of compactified extra dimensions and the observed properties of particles and forces is both a strength and a weakness of string theory. It is a strength because it provides a potential explanation for why the constants of nature take the values they do. The values we observe are determined by the geometry, and different geometries produce different values. It is a weakness because the number of possible geometries is astronomically large, estimated at something like 10 to the power of 500, a number so vast that it has been given the name the landscape of string theory. With so many possible configurations, each producing a different set of physical constants, it becomes extremely difficult to derive specific predictions that distinguish string theory from other possibilities. The landscape problem is one of the most debated issues in theoretical physics. Some physicists see it as a fatal flaw, arguing that a theory which cannot make specific predictions is not a scientific theory in any meaningful sense. Others see it as a feature rather than a bug, arguing that the landscape naturally accommodates the anthropic reasoning we discussed in the context of the hierarchy problem. If there are 10 to the 500 possible universes, each with different physical constants, then it is not surprising that we find ourselves in one where the constants permit the existence of complex structures and observers. The values we observe are not predictions of the theory, but selections from a vast menu of possibilities. Loop quantum gravity approaches the problem from a completely different direction. Rather than starting with strings and extra dimensions, it starts with general relativity and asks how to make it consistent with quantum mechanics while keeping as close as possible to the original geometric picture of gravity. The key move is to take seriously the idea that spacetime is not a smooth, continuous background, but is itself a quantum object with discrete properties at the smallest scales. In loop quantum gravity, the geometry of space is described by a network of quantum states called spin networks. Each node in the network represents a quantum of volume, and each link represents a quantum of area. The smooth, continuous space of general relativity emerges from the collective behavior of these discrete quantum elements at scales much larger than the fundamental quantum of length, which is the Planck length, approximately 1.6 times 10 to the power of negative 35 meters. At scales larger than this, the discrete structure is invisible and space appears smooth and continuous. At scales comparable to the Planck length, the discrete quantum nature of geometry becomes apparent. One of the appealing features of loop quantum gravity is that it avoids the singularities that appear in classical general relativity. In classical general relativity, the equations predict that spacetime curvature becomes infinite at the centers of black holes and at the initial moment of the Big Bang. These infinities, called singularities, are generally understood to be signals that the theory has broken down and that a quantum theory of gravity is needed to describe what actually happens. In loop quantum gravity, the discrete nature of spacetime prevents the curvature from becoming truly infinite. The Big Bang singularity is replaced by a big bounce, a moment of maximum density and curvature from which the universe rebounds, possibly from a previous contracting phase. Black hole singularities are similarly softened by quantum geometric effects. These are genuinely interesting predictions, but they occur at scales so extreme that testing them directly is currently impossible. The Planck length is roughly 20 orders of magnitude smaller than the diameter of a proton, which is itself far smaller than anything current accelerators can probe. Indirect tests have been proposed, including searches for subtle effects on the propagation of high-energy photons from distant gamma-ray bursts, but no definitive signal has been found. What loop quantum gravity does not yet provide is a complete account of how gravity connects to the other forces. It is a theory of quantum geometry, but it does not naturally incorporate the standard model particles and forces into the same framework. String theory, by contrast, naturally incorporates all the forces and particles, but at the cost of extra dimensions, a vast landscape of possibilities, and a mathematical complexity that has made it difficult to extract specific testable predictions. The contrast between the two approaches reflects a deeper tension in theoretical physics between two different strategies for making progress. One strategy is to start from a unified framework and work downward toward observable predictions. String theory follows this strategy. The other strategy is to start from established physics and work upward toward a consistent quantum description of gravity. Loop quantum gravity follows this strategy. Both strategies have produced genuine insights, and it is entirely possible that the final theory of quantum gravity will draw on elements of both, or will emerge from a direction that neither approach has yet anticipated. What is clear is that the Graviton question, the question of how gravity fits into a quantum framework, is inseparable from the question of why gravity is so weak. The weakness of gravity sets the Planck scale, the energy at which quantum gravitational effects become important, far beyond the reach of any experiment we can currently conduct. If gravity were stronger, the Planck scale would be lower, quantum gravity effects would be accessible at lower energies, and we might already have a confirmed theory of quantum gravity. The weakness of gravity is not just a puzzle about force strengths. It is the reason the deepest questions about gravity remain unanswered. Chapter 9. The Landscape of Solutions. The history of attempts to explain gravity's weakness is not a history of failure. It is a history of deepening. Each proposal that has been put forward, whether it has found experimental confirmation or not, has added something to our understanding of what the problem actually is and what kind of solution it might require. Supersymmetry clarified the nature of the fine-tuning problem and showed how a symmetry principle might resolve it. Extra dimensions showed how a geometric relationship between scales could replace the need for fine-tuning entirely. String theory showed how gravity might emerge naturally from a unified framework that includes all the forces. Loop quantum gravity showed how spacetime itself might have a quantum structure that changes the problem at its roots. None of these is a final answer, but together they form a landscape of ideas that has transformed the question from a vague puzzle into a precisely defined challenge. It is worth pausing to appreciate how unusual this situation is in the history of physics. Most of the great problems of physics have been solved within a generation or two of being clearly stated. The nature of heat was clarified by the development of thermodynamics and statistical mechanics over the course of the 19th century. The structure of the atom was worked out within a few decades of the discovery that atoms have internal structure. The unification of electricity and magnetism, the development of quantum mechanics, the confirmation of general relativity. All of these represented profound advances that transformed our understanding of nature, and all of them happened within a recognizable human timescale. The hierarchy problem and the related question of quantum gravity have now been clearly stated for several decades, and a solution remains elusive. This is not a sign that the problem is insoluble. It is a sign that it is genuinely deep, touching something fundamental about the structure of reality that our current conceptual tools are not yet adequate to fully grasp. One direction that has attracted significant attention in recent years is the idea that the hierarchy problem might be connected to the cosmological constant problem, which is in some ways an even more extreme version of the same basic puzzle. The cosmological constant is a term in Einstein's equations that represents the energy density of empty space, sometimes called dark energy. Observations of the accelerating expansion of the universe, first reported in 1998 by two independent teams studying distant supernovae, indicate that the cosmological constant has a small but non-zero positive value. The problem is that quantum field theory predicts a value for the energy density of empty space that is roughly 120 orders of magnitude larger than what is observed. This discrepancy between the predicted and observed values of the cosmological constant is the largest known discrepancy between theory and observation in all of science. The cosmological constant problem and the hierarchy problem are distinct but related. Both involve a fundamental parameter of nature, taking a value that is vastly smaller than what naive theoretical estimates would suggest. Both require either an extraordinary cancellation or a new mechanism that explains why the parameter is so small, and both resist solution within the framework of current physics. Some physicists believe that a solution to one problem will illuminate the other, that whatever mechanism suppresses the cosmological constant to its observed value may also be related to whatever mechanism keeps the Higgs mass small and gravity weak. Others believe the two problems require separate solutions. At present, no one knows. Another direction that has generated interest is the possibility that gravity's weakness is related to the arrow of time and the initial conditions of the universe. The universe began in a state of extraordinarily low entropy, a state of high order and low randomness that has been gradually increasing in entropy ever since. This initial low entropy state is itself a puzzle, because there is no obvious reason within current physics why the universe should have started in such a special configuration. Some physicists have speculated that the weakness of gravity and the low initial entropy of the universe are connected features of the same underlying structure, that a universe with stronger gravity would have different initial conditions and a different thermodynamic history. These ideas are speculative and not yet developed into precise mathematical proposals, but they point toward the possibility that gravity's place among the forces is connected to the larger scale features of the universe's history. There is also a line of thinking that connects gravity's weakness to the existence of complex structures in the universe, including stars, planets, and ultimately life. This is the anthropic line of reasoning applied specifically to gravity. If gravity was stronger by even a modest factor, stars would burn through their fuel far more quickly, reducing the time available for planetary systems to form and for complex chemistry to develop. If gravity was stronger by a large factor, the universe would have recollapsed long before galaxies could form. If gravity were weaker, matter might never have clumped together sufficiently to form stars at all. The value of gravity's strength, on this view, sits within a narrow window that permits the existence of the kind of universe we observe, and we observe it precisely because we are here to observe it. This anthropic reasoning is not universally accepted as a scientific explanation. Many physicists find it unsatisfying because it does not predict a specific value for the strength of gravity, but merely argues that whatever value permits observers will be the one observed. It transforms a dynamical question into a selection effect, and in doing so, it may close off the search for a deeper explanation prematurely. At the same time, it cannot be dismissed entirely. The fact that the constants of nature take values that permit the existence of complex structures is a genuine observation that any complete theory of nature must accommodate, whether by deriving those values from first principles or by explaining why they are selected from a larger set of possibilities. Looking further into the landscape of proposed solutions, there are approaches that challenge even more fundamental assumptions. Some physicists have explored the possibility that the constants of nature are not truly constant, but evolve over cosmic time, taking different values in different epochs of the universe's history. If the strength of gravity were different in the early universe than it is today, the hierarchy problem might look different in that earlier context, and the current weakness of gravity might be a consequence of that evolution, rather than a fixed feature of the laws of nature. Observations constrain how much the fundamental constants can have changed over the age of the universe, and the current bounds suggest that any variation must be extremely small. But small is not zero, and the possibility of varying constants remains an active area of research. There are also proposals that question whether the four fundamental forces are truly fundamental at all, or whether they are themselves emergent phenomena arising from some deeper substrate. In this view, the hierarchy between gravity and the other forces, would not be a property of fundamental physics, but a consequence of the way the forces emerge from more basic structures at different energy scales. The weakness of gravity would reflect not an intrinsic property of a fundamental force, but the particular way in which gravity emerges from the underlying physics at the scales we can probe. This kind of emergent gravity proposal has been developed in various forms, including a proposal by physicist Eric Verlinde that gravity is an entropic force, arising from the statistical behavior of information on holographic screens rather than from a fundamental field or geometric property of spacetime. Verlinde's proposal is controversial and has not achieved broad acceptance, but it illustrates the range of possibilities that physicists are willing to consider when confronting a problem as deep as the hierarchy problem. When a puzzle resists solution within established frameworks for long enough, it eventually forces a willingness to question the frameworks themselves. The hierarchy problem has now been with us long enough that some of the most creative thinking in theoretical physics is directed not at solving the problem within current frameworks, but at identifying which assumptions underlying those frameworks might need to be abandoned. What all of these approaches share, despite their differences, is a recognition that the weakness of gravity is not an isolated fact. It is a symptom of something deep about the structure of the universe, something that connects the physics of the very small to the physics of the very large, the behavior of particles to the geometry of spacetime, the constants of nature to the history and fate of the cosmos. Whatever the final explanation turns out to be, it will almost certainly transform our understanding of physics in ways that go far beyond the specific question of why gravity pulls so gently. Chapter 10. Living with the question. There is something quietly remarkable about the fact that the force we understand best in everyday terms is the one that resists our deepest theoretical understanding. Gravity is the first force we ever named, the first one we described mathematically, and the first one whose effects we learned to predict with precision. And yet, after centuries of investigation, after Newton and Einstein and 100 years of quantum mechanics, gravity remains the odd one out. It does not fit with the others. It does not submit to the same mathematical treatment. It does not reveal its weakness through any mechanism we have yet been able to confirm. It simply sits there, pulling gently on everything, vastly weaker than every other force at the particle scale, and declining to explain itself. This situation is unusual in the history of physics. Science has a strong track record of resolving its deep puzzles within a recognizable time frame. Problems that seemed intractable have a way of yielding when the right conceptual tools are developed, or when experiments reach the sensitivity needed to distinguish between competing explanations. The structure of the atom, the nature of light, the origin of the elements, the large-scale structure of the universe. All of these were profound mysteries that became understood, at least in their broad outlines, within the span of a few generations of scientific work. The hierarchy problem has now been clearly articulated for several decades, and it remains as open as ever. That persistence is itself a clue. It suggests that the resolution, when it comes, will require not just new calculations, but new ways of thinking. It is worth reflecting on what it means to live with an open question of this kind. In everyday life, unanswered questions tend to feel uncomfortable. We are accustomed to seeking resolution, to finding explanations that close the loop and allow us to move on. But in science, and particularly in fundamental physics, the open questions are where the most interesting work happens. They are the places where the map runs out and the territory begins. The hierarchy problem is one of those places. It marks the boundary between what we know and what we do not, And standing at that boundary is not a position of ignorance. It is a position of genuine engagement with the deepest features of reality. The experimental situation over the coming decades will be crucial. The Large Hadron Collider has already pushed the boundaries of what we can probe at high energies, and its ongoing runs continue to gather data that constrains the space of possible new physics. Proposals for next-generation colliders, including the Future Circular Collider, proposed at CERN, and various linear collider proposals in Asia and elsewhere, would reach energies significantly higher than the current Large Hadron Collider, potentially accessing the regime where supersymmetric particles or Kaluza-Klein graviton modes might become visible. Whether these machines will be built depends on political and economic decisions as much as scientific ones, but the scientific case for pushing to higher energies is clear and compelling. Gravitational wave astronomy, opened as a field by the first direct detection of gravitational waves in 2015 by the LIGO collaboration, offers a completely different window into gravity's behavior. Gravitational waves carry information about the most extreme gravitational environments in the universe, including merging black holes and neutron stars, and their properties encode details about how gravity behaves in regimes far from the weak field, slow-motion approximation, where most of our everyday experience lies. Future gravitational wave detectors, including the space-based LISA observatory, planned for launch in the mid-2030s, will be sensitive to gravitational waves from sources across the entire observable universe, providing an unprecedented probe of gravity at cosmological scales. Precision tests of gravity at short distances continue to improve, pushing the bounds on any deviation from the inverse square law to smaller and smaller length scales. If large extra dimensions exist at any scale accessible to these experiments, the deviations they predict should eventually become visible. The absence of a signal so far is informative, but the experiments are far from exhausted, and new techniques for measuring forces at very short ranges are being developed that may push the sensitivity significantly further. Cosmological observations also continue to deepen our understanding of gravity at the larger scales. The nature of dark energy, which appears to be driving the accelerating expansion of the universe, is intimately connected to the cosmological constant problem, and therefore to the hierarchy problem. Upcoming surveys of the large-scale structure of the universe, including the Euclid Space Mission and the Vera Rubin Observatory on the ground, will map the distribution of matter across billions of light-years with unprecedented precision, providing new tests of general relativity at cosmological scales and new constraints on the nature of dark energy. If dark energy turns out to be something more dynamic than a simple cosmological constant, that discovery would have profound implications for our understanding of the vacuum energy problem, and possibly for the hierarchy problem as well. There is also the possibility that the resolution of the hierarchy problem will come not from a single dramatic discovery, but from a gradual accumulation of insights across multiple fronts. The history of physics contains many examples of problems that seemed to require a single grand solution, but turned out to yield to a combination of smaller advances that together change the conceptual landscape sufficiently to make the problem dissolve. The ultraviolet catastrophe in classical physics, which predicted that a perfect black body should radiate infinite energy at high frequencies, was resolved not by a single experiment, but by Planck's introduction of the quantum hypothesis, which changed the conceptual framework in a way that made the infinity go away. Something analogous might happen with the hierarchy problem. The right conceptual shift, perhaps already present in embryonic form in one of the approaches we have discussed, might transform the problem in a way that makes the weakness of gravity look natural rather than puzzling. What would it mean for gravity's weakness to look natural? It would mean finding a framework in which the ratio of gravity's strength to the strength of the other forces is not a free parameter that has to be measured and inserted into the theory by hand, but is instead derived from more fundamental principles. It would mean understanding why the Planck scale sits where it does relative to the electroweak scale, not as an accident or a selection effect, but as a necessary consequence of the underlying structure of space, time, and quantum mechanics. It would mean having a complete theory of quantum gravity that fits naturally with the standard model and explains the full set of observed constants of nature from a small number of fundamental inputs. That goal is ambitious. It may be the most ambitious goal in the history of science, but the history of physics gives reason for a quiet and measured optimism. Every time physicists have pushed deeply enough into the structure of nature, they have found not chaos, but order, not arbitrary complexity, but elegant simplicity at a deeper level. The periodic table emerged from the quantum mechanics of electrons. The diverse phenomena of electricity, magnetism, and light turned out to be aspects of a single unified field. The weak nuclear force and electromagnetism, which appear completely different at low energies, turned out to be unified into a single electroweak force at higher energies. Each of these unifications revealed that what looked like diversity at one level was symmetry at a deeper level. There is every reason to hope that the apparent divide between gravity and the other forces reflects a similar situation, that at some deeper level, or at some higher energy, or in some larger geometric framework, gravity and the other forces are unified in a way that makes their apparent differences at low energies a natural and understandable consequence of how that unity is broken. The weakness of gravity, on this view, is not a defect in the design of the universe. It is a feature of the universe at the particular scale and in the particular corner of the landscape that we inhabit. It is the reason the night sky is dark, rather than blazing with the light of stars that have burned out in seconds. It is the reason galaxies take billions of years to form and stars take millions of years to exhaust their fuel, giving time for planets to cool and chemistry to develop and life to emerge. It is the reason you can hold a magnet in your hand and watch it lift a paperclip against the gravitational pull of an entire planet. Gravity's weakness, for all its theoretical strangeness, is woven into the fabric of everything we know. There is a kind of comfort in that, if you sit with it long enough. The universe is not required to be simple or to arrange itself for our convenience. It is not required to present its deepest structures in forms that are immediately legible to the minds that have evolved within it. The fact that we can ask the question at all, that we can measure the forces, identify the hierarchy, articulate the problem with mathematical precision, and generate a landscape of serious proposals for its resolution, is itself a remarkable thing. We are made of the same particles whose interactions define the forces we are trying to understand. We are built from protons and electrons held together by the very forces we are comparing to gravity, and we are held to a planet by the very force whose weakness we find so puzzling. That recursive quality, the fact that the instruments of inquiry are themselves made of the stuff being inquired about, gives physics a particular kind of depth that is easy to overlook when you are focused on the technical details. But it is worth pausing to notice. The question of why gravity is weak is not just a question about forces and particles and energy scales. It is a question about why the universe is the way it is, why it has the structure that allows matter to persist, stars to shine, and minds to form that are capable of wondering about it all. We do not yet have the answer. The hierarchy problem remains open, the graviton undetected, quantum gravity unresolved, and the deepest reasons for gravity's feebleness unknown. But the question is in good hands. It is being approached from multiple directions simultaneously, with tools and techniques that did not exist a generation ago, by physicists who understand the problem more deeply than any who came before them. The answer, when it comes, will be worth the wait. For now, it is enough to know that gravity, for all its cosmic dominance, pulls on you tonight with a force that a single magnet can overcome. That the force holding galaxies together cannot hold a paperclip to a ceiling without help. That the architect of the large-scale universe is, at the level of the particles it is built from, almost absent, and that somewhere in that strange and gentle feebleness, one of the deepest secrets of the universe is quietly waiting to be understood. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.